Okay, today we're going to start this a new module talking about the fabrication of BioMems devices. The topics are going to be broken up into three different parts. The first part is going to be talking about photolithography. So this is how we can pattern a material using light. So what we're going to see is a lot of the microfabrication processes use light to pattern materials. Okay, and using these techniques, we can actually get down to nanometer-sized dimensions. The question we're trying to ask in this module is how can we make BioMems devices? A lot of BioMems devices are microfabricated, meaning that they're made very small. The reason for this is sometimes the devices need to interact with small organisms, or in some cases individual cells, as we've talked about in the previous modules. So BioMems devices naturally need to be made to dimensions that are similar to cells and other biological materials. The photolithography can be used to make devices quite small. Photolithography techniques have been borrowed from the semiconductor industry. So the same techniques that are used to make your microprocessors that go into your cell phones and computers, those techniques have been adapted to make MEMS devices. MEMS, as you know, stands for micro electromechanical systems. So the types of accelerometers that are in your phones as well, those are made using fabrication techniques that have been adapted from the semiconductor industry. And in fact, the MEMS and the microfluidics field have really grown out of the fabrication techniques from the semiconductor industry. And these techniques are largely based on photolithography, where you use patterns of light to define the features on a substrate. So the first third of it is going to talk about how we can pattern materials using light. The second part will talk about micromachining of hard materials, traditional materials like silicon and glass. So how can we transfer the pattern that we created using photolithography, how can we transfer that into hard materials? And this will make sense once we get into it. The next part is going to be about soft lithography and micromolding. In a lot of BioMems devices, instead of using the traditional hard materials like silicon and glass, we use softer materials like polydimethylsiloxane or PDMS. That's probably the most popular material used in microfluidics research. Also, materials like plastic are used because plastics are much cheaper to make than traditional silicon glass-based devices. You know, a glass chip might cost $10 to $50 a piece. A plastic chip would cost maybe around $1 a piece. And there are even less than that, I would say. And more recently, we're not going to talk about that in this module, but there are paper-based microfluidic devices which can decrease the cost to less than a penny. Okay, so different materials are used in micromachining. There's more of an emphasis on soft materials like plastics and PDMS in BioMems because, as we talked about earlier, in BioMems devices, often the devices have to be disposable. Diagnostic devices, for example, are often disposable. We don't want to reuse them. And in this module, we're also going to be talking about different types of materials used in BioMems. Okay, so the slides, a lot of the slides from this module are from Albert Folk's group, Albert Folk's book. Albert Folk is a faculty member at the University of Washington, and he wrote a very nice textbook called The Introduction to BioMems. Some of the slides will be from there, and some other materials will be incorporated as well. So how many of you have seen, how many of you have worked with photolithography before? How many of you have worked with film photography? Everybody uses digital photography now, right? Okay. Well, photolithography, I would say, was inspired by film photography. All right, the old school cameras, you know, what you did is when you took a picture with it, in the lens of your camera, the aperture opened up, the light came through the camera, and at the back of the camera there's a film, right? Kodak film, if anyone remembers. Kodak film is a light-sensitive material, right? Its properties change when it's exposed to light. In old school photography, what they did is you'd have to take that film into a dark room and develop it, right? Nowadays, everyone's using digital photography. But photolithography is based on the similar principle. Okay, you can define objects or define features by using light, and the basis of photolithography is a photosensitive polymer, like film, that changes properties when it's exposed to light. All right, so the way that a typical photolithography process might work, let's say you start off with the silicon wafer over here. Okay, silicon wafer is typically circular, and the first step is you coat the silicon wafer with photoresist. The photoresist is typically in the liquid form, and you pour the photoresist over the wafer and then you spin coat it. Spin coating means that you'll take this wafer, the wafer is placed on a chuck, and it'll be spun at at 3,000 RPM. Let's say. When it is spun, the liquid will spread out due to centrifugal forces, and you'll have a nice even coat of this photoresist over the surface of the wafer. That's the first step. This is very well controlled because the spin speed, how quickly you spin the wafer, will determine the thickness of the coating on it. Faster spin speeds, thinner coatings. So we have this a nice even layer of this photosensitive organic polymer on top of there. The next thing we do is we do the exposure. So the step 2 is what's called the exposure. This is a selective illumination through a mask. The mask is shown up here. So these dark regions up here. And then you have some dark regions, some transparent regions. This particular mask is showing a very simple pattern where you just have a grid of boxes. Okay, this is not a microfluidic channel, of course. It's just a feature, just to illustrate the idea of photolithography. The main concept here is that light goes through the transparent regions, but it doesn't go through the opaque regions. The parts where the lights go through, the light hits the photoresist, and that changes the properties of the photoresist. Excuse me. There's two types of photoresist. There's a positive and a negative photoresist. A positive photoresist becomes soluble when exposed to light. It becomes soluble in developer. A negative photoresist becomes insoluble when exposed to light. Now, after you expose this to light, you dip this entire thing into a solution of developer, very much like the photographers would use developer to develop the film. Now, when you develop it, what happens is the regions, in the case of the positive photoresist, the regions that were exposed to light, those regions dissolve in the developer and they disappear. All right? They go into the developing solution. So after you pull it out of the developing solution, you have this pattern here. Okay, so you've effectively used light to define your features. As you can imagine, we can make very fine patterns with light. So we can make very small features. We'll get into what the limits of this are. There's actually a limit on how small you can go. We'll get into that later. But this is the basic idea. So any questions so far? Okay. This is a photoresist spin coater. It's used to apply thin films of photoresist for lithography. Like I said earlier, you place this wafer on a spinning chuck. Okay, and the thickness of the photoresist coating decreases with higher spin speed. So this is a typical spin curve. The higher the spin speed, the lower the film thickness. Okay, and the basis behind that is that when the disc is spinning, the centrifugal forces push the liquid towards the outside. The viscosity and the surface tension will want to hold the liquid together. right? So that the opposing forces between the surface tension, viscosity, and the centrifugal forces basically cause the liquid to spread out uniformly over the surface of the wafer. You can buy a lot of these photoresists. They're commercially available. They're very well characterized. As you can see, different types of photoresists will give you different thicknesses. All right, this is the thickness shown on the y-axis. X-axis is the spin speed. You can see that they range from 1,000 to about 8,000 RPM. And the typical thicknesses will be 35,000 angstroms, about 3.5 micrometers, down to 0.5 micrometers. All right, this is an example of a spin coater that we have in our clean room here at Wayne State. So the next step in the photolithography process is this selective illumination, the exposure step. So for doing the exposure step, we use something called the mask aligner. So mask aligners are used in contact mode lithography to align masks and expose the photoresist. So there's a few different modes of lithography. Let's look at this diagram here. The first mode of lithography is called contact mode lithography. So we have the light source up here. The light source is typically some type of ultraviolet light. Ultraviolet light, when it hits the photoresist, it causes the properties of the photoresist to change. It causes a chemical change. It's a light-induced chemical change. We know that light can cause chemical changes in our body. That's what causes sunburn, right? You've probably heard of UV curable glues. When you expose it to UV, the properties of the glue change, the glues harden. In the case of photoresist, when the photoresist is exposed to ultraviolet light, it becomes either soluble in the case of a positive resist, or it becomes insoluble in the case of a negative resist. And both processes can be used. But this diagram is showing the different modes of lithography. So in the contact mode, we have the light source up here. Okay, and that light source goes through an optical system, usually a series of lenses, which collimate the light. Does anyone know what collimation means? Optics guys. Collimation means that the light is parallel. Okay, a typical light source might emit light in all directions, but then the collimation optics will make sure that the light beams are as parallel as possible. Then you have the mask here. Remember that some regions of the mask are transparent, other regions are opaque. So that pattern, whatever pattern is on the mask, that light pattern is then transferred to the photoresist. All right. And this part here is just showing the silicon wafer underneath there. So this is contact mode photolithography. This is probably the most popular form, at least what we use in our research. Then there's proximity mode lithography. Proximity mode is a similar idea, except that there's a small gap between the photoresist and the mask. Okay. The reason why we might want to do that is because the photoresist is sort of a sticky material. If we want to prevent the mask from being contaminated, sometimes we'll keep a small gap in there. And then finally, there's the projection mode lithography. The projection mode lithography uses a series of focusing elements to first first converge the light, and then diverge the light, and then converge it again on the substrate here. Okay, let's look at the. Now, this projection mode again allows it makes sure that the mask does not necessarily have to be in contact with the photoresist. So looking at some of these methods and the advantages and disadvantages, these diagrams and tables are from Professor Yangzhu's MEMS course, which you can take here. He's graciously provided those for this class as well. So contact mode photolithography, some of the advantages is that you can do it with, you can get high resolution. It's a low cost approach. and you can get relatively high throughputs, but the disadvantages is that since the mask is in contact with the the photoresist, the mask can become contaminated, and sometimes the photoresist can be scratched, again just because of the mechanical contact. In proximity mode, you minimize the mask contamination, but you lose resolution. Because let's imagine that there's an opening. If there's an opening in the mask, if there's a hole in the mask, the light will actually spread out from there. It doesn't go straight through it. It actually, because of diffraction, it actually spreads out like a cone. Okay, we'll talk about more about that later. That's actually what limits the smallest feature size in optical lithography. In projection lithography, you get high resolution and you minimize the mask contamination. So it has the advantages of contact and proximity lithography. The only disadvantage is that this is more expensive because you can see the optics for projection mode lithography are more complex. A lot of the industrial lithography systems are projection mode. Okay, they'll use a mask to expose one pattern, and then they'll move the wafer over and expose the next pattern. They'll move the wafer over and expose the next pattern. So this is done in an assembly line manner. When they do this type of thing, they have to make sure that the mask doesn't get contaminated because they're doing one right after another. And they're doing extremely fine features. So this projection mode system, they sometimes called a stepper because it's doing it. It does one step at a time, like one exposure, then another exposure, another exposure. Those are projection mode systems. This is an example of a mask aligner that we have here in the Wayne State clean room. This is the MA6. Typically, what a mask aligner like this would have is that you'd have the mask would be inserted into the device. Again, the mask is something that you design, depending on the device that you're making. The wafer sits underneath there, and the mask aligner presses the wafer up against the mask. Above here is 2 microscope objectives so that you can see what you're doing. Okay. Why would you want to see what you're doing? It might seem like an obvious question, but think about this for a second. If you're making multi-layer devices, why would having these microscopes be useful? Suppose you're going to make a multi-layer device, and you put down one layer and you defined it. This should be aligned. Yes, exactly. The alignment between different layers has to be done. It's done with our eyes, probably. And the 2 microscope objectives are used basically to do an alignment. Okay, imagine that you have 2 patterns, like 2 transparencies, and you put them on top of one another. You want to make sure that the 2 are aligned properly. The way that you do it is you'd make sure that one side of it is aligned, one corner is aligned, and then you'd make sure the other corner is aligned. If the 2 corners are aligned, that means the rest of the sheet is aligned, right? That's why we have 2 microscope objectives instead of 1, so that you can look at multiple parts of the wafer at the same time. Now here you can see like what these little squares are what's called alignment marks. If you're doing a multi-layer device where the layers need to be aligned to one another, typically you'll put like these types of cross patterns on there so that if you align the cross in one layer to the cross in the subsequent layer, that helps you align the 2, just helps you align the different layers together. Okay. Now when we're talking about layers, keep in mind that this type of photolithography process is done repeatedly. What we're doing is we are building an object layer by layer. In one plane, we're defining what it looks like on a 2-dimensional plane, and then we define the next plane on top of that. So we can make complex objects by having multiple steps of deposition and then photolithography. So we'll get to that. We'll get to that later.
So is the majority of that machine really just the alignment portion, not the actual curing and the
Let's take a look at the different parts of the machine here. So this portion down here is the optics. You can see the 2 microscope objectives. This is where the mask sits. Your silicon wafer is placed under here, and the machine will press the silicon wafer up against the mask. This portion here is controlling the exposure. So if you look on top here, this is an ultraviolet light source. That's what those warning signs are. There's an ultraviolet light source here in the back. There's optics up here to make sure that the light is collimated. So what you have coming down here is collimated ultraviolet light. Okay, and according to this diagram here, this is a contact mode lithography system.
Are you aligning it by hand, or you have a machine that's basically you're turning it to?
Oh yeah. That's another good point. The silicon wafer is sitting here, and there's some micrometers, XY micrometers, so that you can move it back and forth, and you can tilt it, change the alignment, just to make sure that it's aligned with the previous layer. So that's why these devices are called mask aligners. If you don't need to do alignment, like this exposure step is actually quite simple. All right. Let's talk a little bit about resists. There's positive and negative photoresists. As I mentioned before, the negative resists become insoluble after exposure, typically due to cross-linking. Positive resists become soluble after exposure through something called chain scission. Let's zoom in here and take a look at some of these things. All right? We talked about the photolithography process already. We have the mask here. All right? The mask has some opaque regions. That's this black area right here. It has some transparent regions that's shown by this white area here. Light is coming through, and then the photoresist is underneath there. All right, the illuminated areas are shown by these crossed lines here, and the areas that are not exposed are dark. So you can see when the light goes through the mask, some regions of the photoresist are exposed. Now, there's two things that can happen. If you have a negative photoresist, after you develop it, okay, negative resists are designed in a way that the areas that were exposed become insoluble. So after you take this thing and after you expose and you put it in a basically a tank full of developer solution, the non-exposed regions will disappear and the exposed regions will become insoluble. This is a negative resist. So in the positive resist, the places that were exposed becomes soluble, and so those regions disappear. So you can see what's happening is that if you're using positive resist, when you design the mask, you have to design what's called a positive mask. The areas that are being the transparent areas are the places that are going to disappear. In the case of a negative resist, the areas that are transparent will remain. So you have to design your mask differently depending on whether you will be using a positive or a negative photoresist. All right, this is also showing the etched film patterns. We'll get to that in the second part, but just really quickly here, one of the ways that you can, we can use light to pattern the photoresist, but the thing that our device is actually going to be made out of may not be photoresist. Let's say we want to make our device out of metal, right? We want to define metal electrodes. What we do is we deposit the photoresist on top of it. Okay, in this case, they're not using metal. They're just using silicon dioxide as the material that they're patterning. Okay, it doesn't matter. There's different techniques to work with different materials. So what they do here is they put the photoresist on top of the silicon dioxide. They do the exposure step, and then they can transfer the photoresist pattern onto the underlying silicon dioxide layer by doing something called a dry etch or a wet etch. We'll talk about that later. The point here is that you can transfer the photoresist pattern to a layer underneath it. Okay, so that way you can make things. You can make things using photolithography. They don't necessarily have to be made out of photoresist. This is yes.
Why does the mask pattern face down?
Why does a mask pattern face down? That's a good question. Can anyone think of why? So the question Is you, remind me your name?
Shirley.
Shirley.
Shirley? Oh, you can call me Shirley.
Shirley. Okay, sure. Shirley's easy. So Shirley's asking why are the mask patterns on the bottom of the mask rather than the top? You actually know the answer to this because we hinted at it in the previous slide.
So you're not losing the parallel rates.
Exactly. The closer the pattern is to the photoresist, the better off you are. So these patterns here will typically be made out of metal. There'll be a thin film of metal deposited on the mask itself is made of glass, but the opaque regions are metal, and the transparent regions they have no metal on them. Yeah, so the metal is actually facing the photoresist, so that you get sharper features. So let's look at the negative resist. Again, the negative resist becomes insoluble after exposure, typically due to something called cross-linking. Cross-linking is, for those of you from a chemical engineering background, you know this, but a lot of polymers just make a really rough sketch of what cross-linking is. Because this is important for other things too. So, one very general way we can think of polymers is as strings. Okay, they are strings they're chains of a chemical material. For example, a very common type of structure that we see is carbon chains. One carbon atom bonded to another carbon atom, and then they have these different groups attached to these different sides of the molecule. But the point is, this is like a chain, okay? And a lot of polymers are not necessarily just carbon chains; they're made of other chains. The point is, there are these long strings of molecules. Now, if you have a whole bunch of monomers in solution like this, they might be in a liquid form. The physical properties of a polymer, if they're in monomer form, they will be in a liquid form. But if you expose this to ultraviolet light and there's something called a photoinitiator in that solution, what will happen is that you can form bonds between these different groups that hang off the end of the polymer. Now you have something like this where you have these strings, but these strings are attached together by these things called crosslinks. This causes the material to harden. This is a very hand-wavy description of what cross-linking is. There's a lot more detail in that, but I just want to give you what the basic idea is. Okay, so what you're doing here is by exposing the polymer to ultraviolet radiation, you are cross-linking the material. All right, and so what you see here on the left, this is called cross-linking. The ultraviolet light generates something called free radicals in the material, and the free radicals react with the polymers to cause them to cross-link to one another. That increases the effective molecular weight, and that renders the resist insoluble. Other things that can happen is that the ultraviolet light can generate hydrophobic or hydrophilic groups, which can also change the solubility properties of the material. But at the end of the day, the regions that were exposed become insoluble in the developer. Now, the developer obviously has to be chosen properly. There are different types of developers designed for positive and negative photoresists, and those developers are typically commercially available. Now, if we go to the positive resists become soluble after exposure, and one mechanism of this is something called chain scission. Polymethyl methacrylate is a material. It's an acrylic glass-like material, which is also transparent, which is has the properties that it has a positive photoresist-like properties. So you can see from this chemical diagram that when this molecule, shown on the left, is exposed to ultraviolet light, it undergoes a chemical transformation in these carbon bonds here that cause it to break into two separate groups. Okay, and when it breaks into those two separate groups, now the material has become soluble in developers. When you dip it in the developer solution, this disappears. All right. So a lot of times, as engineers, we may not know the details and the stoichiometry, all the details of the chemistry about how it works, but we do know that ultraviolet light or various types of light can react with materials and change its chemical properties. So that is the basis for photolithography and a lot of the light-based patterning techniques that we'll be talking about in this class. This chart, it might be a little bit hard for you to see right now, but in your printed notes, you'll be able to see this better. This is just a comparison of positive and negative photoresists, some of the properties. So typically, positive resist is more expensive, negative resist is less expensive. Positive resists usually have an aqueous-based developer, right, which is more environmentally friendly. Negative resists typically use some type of organic solvent, which needs to be disposed in a more careful manner. One of the advantages of a negative photoresist is that once that negative photoresist is exposed, it can become very strongly cross-linked, and that makes it very, very insoluble. By contrast, in a positive photoresist, the difference between the exposed and unexposed regions in terms of their solubility, so how soluble the exposed region is versus the unexposed region, there's less of a difference. So when you go to develop it, you have to be more careful if you're dealing with a positive photoresist. Also in terms of process windows, with negative photoresist, you have to be a little bit careful about oxygen and humidity. So one of the reasons why the clean room has very controlled humidity and temperature conditions is because these photoresists are, they're quite sensitive to different environmental conditions. Okay. The humidity has to be controlled. The temperature should be controlled properly. I've heard of horror stories when grad students at one university are not able to repeat the experiments at other universities because the humidity was a little bit different in one clean room versus the other. So a lot of these processes do have to be optimized properly. With positive photoresists, you can get very small feature sizes, 0.5 micrometers and below. With negative resists, a plus or minus 2 microns is typical. I think you can get smaller than that now. Let's see. One thing you do have to be careful about in negative photoresist is the swelling. If you keep even a negative resist in developer for too long, the photoresist patterns will actually swell, and when they swell, they can come off the wafer. Okay, so these little things that you have to be careful about. From a purely theoretical standpoint, none of these will really matter that much or make that much sense to you until you actually go in the clean room and make your device. And just doing one photolithography step is taking you weeks because these little details are driving you crazy. That being said, a lot of these things have been, there are process recipes for all the photolithography steps to help save time. So, the places like Intel, which are doing, photolithography steps, big foundry places like TSMC, they have these processes optimized down to down to a science. Their processes and down to the type of water they use, to the temperature, humidity, everything is very, very well controlled. The book also mentions some information about biocompatible photoresists. With BioMems devices, oftentimes we're trying to make patterns and devices that interact with cells and biomolecules. Now, for that reason, we have to make sure that the materials themselves are biocompatible. Unfortunately, a lot of photoresist materials are made from organics or non-organic materials that are not compatible with cells or biomolecules. They're toxic. Okay. So as a result, there have been a number of biocompatible photoresists which have been developed. And here are a few examples. I should mention another reason why this typical photoresist processing is not very biocompatible is because of the solvent steps. You have to take this thing and you have to put it into this developer solution. And that developer solution may be an organic solvent or it'll be a strong base or acid. So this is obviously not compatible with living organisms. For that reason, there have been some of these biocompatible photoresists that have been developed. There are many of them. There's, you could spend an entire semester talking about biocompatible photoresists, biomaterials. Dr. Sundaragavan at the BME department teaches a class in biomaterials. She does spend a semester talking about various types of biocompatible materials. Now, a few examples here of biocompatible materials which can be patterned using light. As this one example is polynipam. It's a water-soluble biocompatible photoresist. And this one works in a slightly different way in the sense that the exposed areas dissolve at higher temperatures. So as a previous photoresist, it changed the solubility properties. It made it either soluble or insoluble. In the case of this material, exposure to the light changes the temperature at which the material dissolves. The exposed areas will dissolve at higher temperatures than the non-exposed areas. So how can you process something like this? You'd start by coating the photoresist on glass, and then this is all done in an aqueous solution, so it's very biocompatible. After ultraviolet illumination, ultraviolet induces a chemical change here. There's a photocleavage that happens, and that changes the properties. Then what you do is you change the temperature. Notice that we're going from high temperature to lower temperatures here. Now, as I mentioned, the exposed areas dissolve at higher temperatures. All right, so these are dissolved, but the non-exposed areas remain when we cool it. All right, then you go to this step D. Now, what they're doing here is that they're showing that you can actually pattern a biomolecule using this approach. So they put this in a solution containing proteins. What they're trying to do here is they're trying to pattern proteins, as they have done here in this micrograph. So the proteins will attach to the glass substrate or the glass chip underneath here, and proteins actually like to attach to glass, depending on what type of protein it is. So these proteins can physisorb on the surface, and there's also some protein on top of the photoresist. Now when we do the second cooling, you go down to even lower temperatures, this photoresist resolves. This layer of photoresist resolves, and that takes the protein layer on top of it with it. So you're left with a nice pattern of proteins, as you can see here. All right. So you couldn't do protein patterning like this if you had to use a traditional photoresist and a traditional development solution, because it would destroy the proteins. So other examples of biocompatible materials. This particular material is commercially available. It's FDA approved as a dental implant, but it has this. It's basically a UV curable acrylic type material. It's a negative resist, meaning that the regions that are exposed to light cure, and then you have to heat it up also to 170 degrees Celsius. Again, some dental implants use this. There's also photosensitive PDMS, polydimethylsiloxane. This is a very popular material that's used in microfluidic devices. We'll talk more about this. Later.
So you're not heating this material up. It's just whatever temperature, room temperature, and then you're cooling it. It doesn't show like a heating step at all.
Oh, so what's happening is that you're actually you're exposing the system at a higher temperature, and then you're bringing the system down to cooler temperatures.
So you heat it before you actually have to heat it.
Yes, that's right. Because interestingly, this material is a thermally sensitive resist, meaning like the exposed areas dissolve at higher temperatures. Here's some examples of photoresist structures after development. You can see you get some very nice patterns on these devices. Okay, this is actually showing like three-dimensional photoresist structures. Two-dimensional structures look like this. They're similar, simpler. This is actually showing some tricks that you can do by doing 3D exposures. So we can take a quick look at how this process works. So this is using two types of photoresist. Can everyone see this here? LOR stands for lift-off resist. It's actually a type of photoresist that dissolves very rapidly. So you put a layer of this lift-off resist on there first, and then you put a layer of thin photoresist. This is a typical photoresist. And you expose the upper layer of photoresist, and then you go through a development step. Okay, and that leaves the LOR layer underneath. But the LOR layer is patterned. Okay, so you have a patterned layer of this photoresist, which will dissolve and develop quite rapidly. Then you spin another coat of thick photoresist on top of it, and you do what's called a shallow exposure. Now, a shallow exposure means that we only expose for a short period of time. Okay, one of the variables that we have in our control, one of the parameters that we have in our control is how long we do the exposure. Another parameter is how long we do the development. Okay, so when this says shallow exposure here, it means through the mask we're only going to expose it for a short period of time through one mask. And then through a different mask, we do a deep exposure, means we expose for a long period of time. When we expose for a longer period of time, the patterns which are exposed, it goes much deeper into the photoresist. So a deeper portion of the photoresist becomes exposed and insoluble. Okay, so in this case, the regions that were left here are the regions that were not exposed to that were not exposed. Okay, so you can get some various three-dimensional structures this way. All right, this is a more complicated procedure for making three-dimensional photoresist structures. The basic method would just be a single mask, a single exposure, and you basically make two-dimensional patterns. All right, this is just nice because you can see how small these features can be, and you can actually get features much smaller than this. This is showing a 30 micron gap here, like a 30 micron wide device. You can make various types of structures that look like this, and depending on, we'll talk about this, but this type of process can get you features down to a fraction of a micrometer, into the hundreds of nanometers, even below 100 nanometers if you use very small wavelengths of light. So SU8 is a material that was introduced by IBM in the late 90s. This is a negative photoresist. is very popular. You'll see it in almost every microfluidics lab. The reason why it's popular is that you can make thick layers, and you can also make high aspect ratio layers, high aspect ratio exposures. So I'll explain what that is. Most of these photoresist materials, the typical ones, positive and negative resistors, these were the materials, again, these came from the semiconductor industry. In the semiconductor industry, they're not really interested in making thick layers. In fact, they want the layers to be as thin as possible. The different metal layers that go on a microprocessor, those are going to be very, very thin layers. Okay. But when we're dealing with microfluidic devices, these patterns that we're making on the photoresist are going to define microfluidic channels. Microfluidic channels have dimensions on the order of anywhere between 100 microns down to maybe 1 micron or so. Nanochannels have even smaller dimensions. But often, a lot of folks working in the microfluidics area want dimensions around 100 microns to 50 microns or so. The resists made for semiconductor fabrication typically have thicknesses on the order of 2 microns, 3 microns. Okay, so it's too thin for making microfluidic channels. You can make channels, but they'll have a very large hydraulic resistance because they're just so narrow. They're very thin and narrow. So SU8 can be spin-coated, very much like regular photoresists, but it's more viscous. It's a thicker type resist, and so it can be, when you spin-coat it, it spin-coats into a thicker layer. Typically anywhere between 25 micrometers all the way up to several hundred micrometers. This is a good range for microfluidic channels. You can expose SU8 at 365 nanometer light, which is readily available. It's in the ultraviolet range, but you can easily find these types of bulbs. It has this property that you can get very high aspect ratios. What is aspect ratio? This is one of the questions in your homework, by the way. It's the height of a feature divided by its width. For example, this is one of the pictures that Microchem, the company that makes SU8, they like to show. Very tall structures here. Okay, this is probably the aspect ratio is defined as the width. I'm sorry, it's defined as the height of an object divided by the width of the object. So the aspect ratio here, you can just estimate here that it's about, I would say it's about 7. If you can make very tall structures, this is good. If you can make very tall and narrow structures, this is good for a number of reasons. One reason is that it improves surface area. This is one of the questions in your homework as well. The taller you can make these structures, the better off you are. It's a hint on your homework question. The other thing is, if you want to make your microfluidics channels very tall and very narrow, this material is useful to do that. And in fact, that's often the case in microfluidics where you want to make tall and narrow channels. For example, things like Dean flows take advantage. Dean flows can be used to separate particles based on size. Some of the Dean flows actually rely on tall channels to control the intensity of the Dean vortices. Okay, we're not going to get into that now. One thing that happens with some types of photoresists is that, let's say you have your mask looks like this, and your photoresist is sitting underneath here. When the light goes through this mask, it actually starts to spread out a little bit. Okay, and so this is your mask. And this is your photoresist sitting right underneath there. And this is your substrate. Okay, so when light goes through the mask and it starts to spread out, it can actually result, after development, it can result in features that look like this, right? So this is your photoresist. And this is your substrate. So after development, it'll look something like that. Now, one of the nice features about SU8 is that it actually retains these nice vertical sidewalls. So it will turn out more like this, more like you intended, if you have a material like SU8. All right. When you have nice vertical sidewalls like this, it actually enables you to make nice tall and narrow structures like this. Okay, so you can see that this problem here, this problem of the light spreading out, it's a multifaceted issue. Okay, so some of it has to do with the chemical properties of the photoresist. A lot of it also has to do with the optics of the system. If you can somehow make sure that the light is more collimated so it doesn't spread out, you have less diffraction, then you'll also be able to get smaller and well-defined features. It turns out, from the optical standpoint, one way you can get very tall structures is to use high energy light. High energy light tends to bend less. Okay, but that means you have to use X-rays or gamma rays and things like that. And those, they have those types of systems like synchrotrons, for example, are systems that can generate very high energy beams of light, and they're used in lithography, and they can get aspect ratios of 10 or more. I think they can even get into the 50 range. Okay, but those systems are very expensive. There's only, the synchrotrons, like you have to actually send your device into a national lab to have it exposed, right? Those types of systems are quite complicated. So one of the nice things about SU8 is that you get these very high aspect ratio structures. It's a commercially available material. A lot of microfluidics labs have this material on hand. Okay. The developer for this is polyethylene glycol, and there's a very high selectivity between the developed and non-developed regions, which means like when you put it in the developer, you don't have to time it perfectly. You don't have to be like 35 seconds or 65 seconds, and then I must take it out right at that time, or else I will have like overdeveloped some patterns. It's a pretty robust material. So even if you're off by a little bit in terms of timing, it's okay. A few slides here just to show some tricks that you can play with photolithography. Typically, in 99.9% of the systems, you're going to expose light from above. Okay, but you can play tricks with this. You can do tilted exposures to get tilted structures because the light is coming in at an angle here. If you do two tilted exposures, you can get structures that have a V shape. If you rotate while the ultraviolet light is coming in, if you rotate the device, you can get cone-shaped structures. And if you tilt the system and you also have a reflective coating on the bottom that causes the light to reflect back up, then you can make even more bizarre-looking structures. Okay. Basic idea is still the same, like that the regions that are exposed to light, they get exposed and they become, in this case, they become insoluble in the resist. So you can get creative. However you put the light on there, you will get structures like this. We'll talk about the limits of optical lithography after we take let's take a 3 or 4 minute break, and then we'll talk about the limits here. Right. So any questions so far on optical lithography?
So do the masks last? So depending on what type you use, your mask will last longer or shorter period of time?
Depending on which type of lithography you're going to use, like the longevity of the masks is what you're asking about? Well, I think, like it depends what type of mask you have. There's like the, standard masks are made from you have a glass plate, which is transparent to ultraviolet light, and then on top of that you have these patterns of chrome, metal patterns on it. Basically, the opaque regions, the metal regions, don't allow light to pass through.
Okay.
So those masks are pretty robust. Even if they're contaminated with photoresist, you can clean them, just by putting them in acetone. There's also like the poor man's mask, where you literally like take a printer and you print out a transparency. You can make a mask out of just printing out a laser printer, a transparency. Those are called transparency masks, and they don't have the resolution of the chrome masks. With chrome masks, you can get down to sub-micrometer dimensions. But with film masks, you can get maybe 10 to 50 microns. With the cheap laser printer, you're going to get larger than that. But the high DPI laser printers, we get our film masks done at a company out in Colorado. They can get down to 10 micron feature size. When we're talking about lithography, this is sort of a segue into this. Like when we're talking about lithography, we're often interested in the minimum feature size. Okay, I think I had shown you in the first module, I'd shown you a chart of Moore's law, right? I said that the transistors are getting smaller and smaller as we go in time. Now, the reason why in the electronics industry they were miniaturizing it is that by packing more transistors on a chip, you could get more complex functionality that the processor could do, more calculations, and also, as it turned out, the speed of the transistor improved when you made the transistor smaller. And also the power consumption per transistor decreased when you made the transistor smaller. There was a lot of benefits towards miniaturization there. So what was happening is that the optical lithography was the people, the manufacturing engineers, the process engineers, were trying to make optical lithography better. Okay. So from a fundamental standpoint, we run into this problem here. Okay. You have a mask. Well, it's better shown in this picture here. If you were to take a laser and shoot it through an aperture, this is a simple physics experiment which many of you have probably done. Either slits or apertures, you put a light source through there, and you notice that you make diffraction patterns like this, right? This spot here is not necessarily the width of the laser beam. It's not necessarily the size of the aperture either. It's larger. There are these diffraction patterns that form, and this width here, the width of this region here, is due to the diffraction of light. Okay, you can think about this as the light is, the light sort of spreads out once it goes out from the aperture. And this is what increases your spot size. Or you can think about it in terms of diffraction, treating light as a wave. There's some constructive and destructive interference patterns that occur in creating like this disc-like pattern that you see here. This is from Hyperphysics, by the way. You can tell I really like this website. Diffraction leads to something called the Rayleigh diffraction limit. Okay. Even if you were to make this pinhole very small, we're talking about masks here, right? In the masks, you're going to have regions of transparent and non-transparent regions. If you make one of those transparent regions very, very tiny, so that hoping to get a very small feature size, the diffraction will ultimately limit you in how small a feature that you can make. All right, and that process is actually quite well understood. Due to Rayleigh diffraction, the minimum feature size and the depth of field, we'll talk about that later, is proportional to the wavelength. So MFS, the minimum feature size, is equal to K1 times the lambda, the wavelength of the light, divided by the numerical aperture. The numerical aperture has to do with the optics of the system. Okay, the larger the numerical aperture, the smaller the minimum feature size. Typically, with commercial devices, the numerical aperture is somewhere between 0.5 and 0.6. Can be outside that range as well, but that's the general range there. In the perfect system, the minimum feature size would simply be lambda divided by the numerical aperture, but because no system is perfect, There are, there's always like some type of alignment issues, and you can never get a perfect point source beam and things like that. Because of that, there's a fudge factor. There's just this constant K1, which kind of takes into account all those imperfections in the system, and that K1 is about 0.5 to 0.8. So the minimum feature size is given by this equation here. So the important things that we notice as an engineer are the ones that we can control, right? We'd obviously want to make K1 as small as possible, right? We also want to make the numerical aperture as large as possible, but the problem is if you increase the numerical aperture, you also reduce the depth of field. All right, so the depth of field, like how high you want to make your feature size. If you want to have some height to that feature, you can't have too small a depth of field. So it's sort of a trade-off that people have to look at. In general, what they try to do, you notice that the numerical aperture is squared at the bottom, so it plays an important role there. Now, if we just talk about minimum feature size, right? You can see that if we want to get minimum feature size, one of the ways we can do it is by just using a smaller wavelength of light. And this is what the industry has been doing, has been pushing for the last 10 to 15 years especially. So making smaller feature size requires a smaller lambda. Conventional ultraviolet lithography started around 360 nanometers all the way up to 450 nanometers. Well, 450 is actually in the blue light range, but 360 to 400 nanometers it was starting off with. Now industry has been pushing for what's called deep UV, extreme UV. So these light sources have a smaller wavelength. Right, this is a map from that was published by TSMC. TSMC is Taiwan Semiconductor Manufacturing Corporation. The semiconductor industry is the one who's pushing this because they're the ones who really have, there's market demand to make transistors smaller. This is a slide from a conference in 2012 where they were showing different tools used for optical lithography. And by tools, they're talking about this laser here, which they start off with 193 nanometer lasers. Okay, and then now they're moving to, a lot of companies like Intel are moving to extreme ultraviolet, EUV. This can get you down to 13.5 nanometers in feature size. And then a newer not a newer technology, but an alternative technology is to use electron beams instead of photons. Okay, when we're talking about light, we're talking about photons. Okay, and this Rayleigh diffraction limit has to do with the wavelength of the photon or the electron. Turns out electrons can have a much smaller wavelength than photons can. So that's why electron beam lithography can get you down to even smaller sizes. So this chart was basically showing the resolution in nanometers on the y-axis and the different technologies. So, so with this laser, for example, this line shows you different this line shows you like different resolutions that you can get with this tool. And you can see what they're doing here is they have tools that have different numerical apertures, 0.85 all the way up to 1.35. So you can see that they have quite a large numerical apertures that they're using here. And they also have optimized their system so that that K1 that you see up here, the minimum feature size is K1, they try to make that K1 as small as possible. They do the same thing with the extreme ultraviolet. You can see that the numerical apertures here are a little bit smaller, but ultimately you can get smaller feature sizes. And then with electron beam lithography, they just have different processes that use electron beams to get progressively smaller devices. So I'll talk about.
Are some of those technology increases leveraging MEMS technology, like getting better lasers?
Oh, are you talking about this one here? Yeah, these basically are different lasers. This laser is, I believe it's argon fluorine. It's 193 nanometers. So the light source is 193 nanometers. Then extreme UV, the light source is 13.5 nanometers. So they're basically going to smaller and smaller wavelength light sources. Of course, this makes the process much more expensive because when you're working with high energy light sources, they're more dangerous. The optics have to be tuned towards those wavelengths. You know, most of the optics that we buy, like my glasses, they're only designed for visible wavelengths. You have to get special optics that are designed for made of materials that are transparent to ultraviolet. Okay, and electron beams are a completely different animal, so we'll talk a little bit about that in the next slide. Point is here that there is a limit to optical lithography in terms of how small you can make a device. Right now, the limit is somewhere in the tens of nanometers range. Very hard to make things smaller than that. Yes?
Why is the numerical aperture of EUV is even smaller than the argon?
Yeah, that's a very good question. I was actually thinking that myself. The question was, why is the let's go back up here. Why is the numerical aperture for EUV only 0.42, while the numerical aperture for argon fluorine is much larger? I have a feeling it has to do with the optics. It's like I was saying, like when you're dealing with very small wavelength lasers, the optics have to be designed differently. You have to use different materials for the optics. For example, a lot of materials, a lot of glass materials, like they'll absorb strongly in the ultraviolet region. You have to get special, like quartz glass, which is UV transparent, and even quartz will absorb at smaller wavelengths. So the optics for EUV maybe hasn't quite caught up to what the optics for 200 nanometers are. And that would be my guess. So one way to sort of work around this, it's not the perfect solution because, as we'll see, E-beam lithography is a serial write process. One solution about getting around the diffraction problem, since the diffraction is limited by the wavelength, as we can see here, right? So how can we get something with very, very small wavelength? Well, it turns out electrons, if you use electrons instead of photons, they can have much smaller wavelengths. They can have wavelengths in equivalent wavelengths in the angstrom range. You can calculate these using de Broglie's equation. But the higher, electrons have this thing where they behave as a wave and as a particle. There's wave-particle duality, and you can calculate the equivalent wavelength by using something called the de Broglie equation. The higher the energy of the electron, the smaller the wavelength is going to be. So if you accelerate an electron that's to a very rapid velocity, it'll have a smaller equivalent wavelength. So electron beam lithography uses electrons to pattern photoresists instead of photons. So the resolution an E-beam depends on, ultimately it's not, with E-beams you're not limited by the wavelength, by the diffraction limit. Most of the time you're actually limited with the beam size. Okay, so it's possible to get smaller than 10 nanometers with E-beam lithography, but the systems are more complicated. They require high vacuum, and it's slow because it's a serial write. So let's look at what this means. This is a schematic of a scanning an electron lithography system. So like I said, instead of having a light source, you have to have an electron source. So up here at the top, you have something called an electron emitter. An electron emitter could be something as simple as a filament that's heated. Tungsten filaments, for example, if you heat them, they will actually give off electrons due to something called thermionic emission. These types of filaments were used in the old-style TVs, the big CRTs, cathode ray tubes. Cathode ray tubes actually shot electrons to the glass, and the glass was coated with phosphor, and that would make the phosphorus glow. Right? So those things actually had electron guns inside them. Now, electron guns, they have to be in vacuum for them to work. But it's basically like a filament that's heated up and it gives off electrons. Okay, once you have given off the electrons, then you have to accelerate them towards the substrate, towards your photoresist. So your substrate is sitting here at the bottom at the bottom here. So you want to shoot electrons into there. So with electrons, now think about this, with photons, with light, we use like typical optics, right? We use lenses and things like that. Okay, and the photons will diffract or bend at the interface between the lens and the air, right? But with electrons, what we have to do is we have to use electric fields. So we use these things called electrostatic lenses. And they're basically like, they're sort of like concentric rings. And those rings are, you apply a voltage to those rings and it generates an electric field. Electrons are negatively charged, so they will, there's a force, there's an electrostatic force that's exerted on those electrons. And you can manipulate those electrostatic forces. You can design these electrostatic lenses in a way to focus a beam of electrons. So, for example, here you see the electrons are spreading out and going out in all different directions. This electrostatic lens condenses them together. This particular electrode is called a blanking electrode. By applying an electric field, you can basically cause the electrons to go in a different direction completely, so your photoresist doesn't get exposed. It's kind of like an on-off switch. If you don't want the photoresist exposed, you can turn on this blanking electrode and send the electrons off to a different direction, so they don't hit the photoresist. You have like second, the condenser lens, and then you have this thing called a beam limiting aperture. It's basically a small hole so that the electrons come out in a pseudo column. And then you have more basically electrostatic optics to help shape the electron beam. And then you have a final lens to focus that beam down into the substrate. So like I said, with the Rayleigh diffraction limit, the wavelength of electrons is in the angstrom range. It's really tiny. So you're not diffraction limited. What you're limited by is just these optics here and how finely they can focus the beam. It's a completely different system. So electron beam systems are actually quite expensive. This is a company that's well known for their electron beam systems. It's called Wraith. It's a company called Wraith. This is what a typical tool looks like. This whole thing is under vacuum. And these different parts sticking out of it. One part is the electron gun. Another thing here is kind of like a detector, so you can see what you can actually see. You can take images while you're fabricating things. And there's this is all computer controlled, so that you send in your CAD file, and the e-beam system will basically scan that electron beam back and forth to make your pattern. So notice that this is very different from a mask. In the mask type system, as we saw earlier, just to be clear here, we're shining ultraviolet light through a mask which is transparent in some regions and opaque in other regions. In the case of the electron beam, what you're doing is you just have a single beam, and you're actually scanning that beam. You're raster scanning it back and forth across your photoresist. And in the regions and this blanking electrode is controlling whether your beam is on or off. So you're basically going spot by spot and turning the beam on if you want to expose that spot, that pixel, or turning the beam off if you don't want to expose that pixel. So this is a serial write process. It doesn't require a mask, which is nice. It's a maskless process, but the disadvantage is that since you have to raster scan that beam, it's a slower process. Okay. So e-beam lithography is used a lot. You can see that this company, Wraith, does quite well for itself. Their electron beam systems are in every major fab and many universities. We have an electron beam system here, actually, at Wayne State in the chemistry department, and we have focused ion beam system here, which I believe has e-beam capabilities as well. These are some examples of devices that you can, or features that you can define using e-beam. You can see that this scale bar here is 10 microns. So you can make very, very fine features with an electron beam lithography system, much better than you could do with optical lithography. Questions on e-beams? Yes, wow.
Does DRIE equals in e-beam lithography?
DRIE is called deep RIE. That's a different process. We'll get into that in a second. So just to clarify, the processes that we're talking about here is just lithography. The question that we're trying to answer here is, how can we pattern materials using light? The next part will be, how can we transfer those photoresist patterns onto a different material? So we'll talk about reactive ion etching, deep RIE, and so on later. Yeah, good question. So I mentioned that E-beam lithography is maskless. Okay, so maskless means you don't need a mask. Instead, what you do is you scan that electron beam to various parts of the resist and either turn it on or off and expose each pixel individually. So you don't necessarily, if you want to do maskless lithography, you can also do it with a laser. You can imagine taking a laser, scanning the laser beam around, exposing or not exposing certain regions of the photoresist. But as we said, with E-beams, you'll get much, much higher resolution. Of course, E-beams are also much more expensive. This rate system probably costs millions of dollars. I don't have a specific number on it, but I know it's over $1 million. There are some laser-based systems which basically raster scan a laser, and you can expose photoresists that way. This is an example showing the raster scanning of SU8. This image is from the Folk textbook. You can see you can get some nice feature sizes this way. This thing actually shows something else interesting that doesn't have to do with maskless lithography per se. It could have to do with any type of lithography. Is that what we're seeing here is we're seeing the height of these structures are the same, but as we go to the left, we're seeing the structures are getting progressively more and more narrow. Okay, so the aspect ratio of the structures is increasing as we go to the left. One of the things that happens when you get very high aspect ratio structures like this looks like it's like beyond 10. Then you have tall, narrow structures. They can become mechanically, mechanically compliant, and you'll lose some of the structural rigidity and the integrity of the structure. So you have to be careful if you're trying to do very tall structures, very tall and thin structures this way. So one of the disadvantages, as I said, if you're doing maskless lithography with a laser or an E-beam, you have to raster scan it across. So it takes some time to do. Another way of doing maskless lithography, which is actually quite nice, is using a digital micromirror device. So we talked about DMDs in the last module. It's a MEMS device, very, very cool device. They sell a lot of them for projecting movies. Okay, in fact, this this projector here is not with a micromirror device. They use a 3 LCD panel, but a lot of projectors are DLP projectors. The ones that you see in the movie theaters are often made of micromirror arrays. Turns out that these DMDs can project light patterns, right? They're very good at projecting light patterns. So why not use them for lithography? So this has turned out to be a pretty successful idea. Micromirrors, as you know, like the idea is that you point light at the micromirror. You have a beam of light that's pointed at the micromirror. Look at this here. Now this schematic here is a little bit simplified. Okay, what you'd actually have is a light source somewhere around here, and that light source would be pointed at the micromirror array. So the light would go something like this. And the micromirror array, each one of those mirrors can be either in one position or the other position. As a result, the projected light will have a pattern going out this way. All right, so each one of these pixels will appear light or dark, depending on what angle the mirror is at. All right, so you're basically projecting a light pattern, much like this projector is projecting on our board up there. You're projecting an ultraviolet light pattern into the system. This goes into a mirror, and it goes into a projection lens, and that projection lens projects that pattern onto an ultraviolet curable resin. Okay, this is a resin is like a liquid. Okay, that liquid, it's like a UV curable glue. When that liquid is exposed to ultraviolet light, it hardens into a solid. They have their device, what they're patterning, they have it attached to, it says an elevator here. All right, so you expose one thin layer, and then you move the device down, and then you expose another thin layer. And then you keep on doing that, and you can get three-dimensional patterns that way. So these are examples of some very beautiful three-dimensional patterns that you can get by using this lithography process. Now, key difference, there's a few big differences between this micromirror type device and a traditional photolithography. First, you notice that you don't need a mask, right? The micromirror is creating the pattern of light and dark for you, rather than having to print a mask. So that's great. The second thing is that, you know, in this three-dimensional process, you can see that you can make any arbitrary three-dimensional structure. You know, because you're exposing one layer at a time, and these layers stack on each other, you can create some very beautiful three-dimensional structures. So this is similar to what's called stereolithography. Stereolithography is where you are, basically you have a UV curable resin, and you have a light source that you're sort of pointing and projecting at different areas of that resin to make a 3D object. All right, a lot of you have heard a lot of buzz about 3D printers. How many of you have heard about 3D printers? Okay. Yeah, you can buy. I was told today that you can buy a 3D printer for $250 now, a cheapo version of one. You know, it might not have great resolution. The higher end one go for thousands of dollars, but it's quite amazing what you can do. So those aren't using lithography, but they're not using optical lithography. They're just extruding a piece of melted plastic from a tip, and that tip is sort of moving around and printing devices. Maybe I'll talk about that briefly at the end of this module. But this is nice because you can use these types of light to pattern things in a three-dimensional form, and it's a very scalable process. And these systems obviously are not cheap, but they can make some very complex structures. Yes.
What's the first depth that you? So that elevator, it's in the liquid, it's in the resin,
Mm-hmm.
and then it kind of goes down. So is there a minimum depth that first layer as it goes down?
Oh, the question is what is the minimum depth of like this layer right here? Well, that's controlled by the z-axis stage. So with piezoelectric, if you have a piezoelectric stage, you can control that to within nanometers if you'd like. You can make very, very thin layers this way. Yeah, you're not limited by the z-axis. What you'd ultimately be limited by is the fact that, you know, your optics has a certain depth of field. Okay, this is getting back to that depth of field that we talked about earlier. You know, when this area is being exposed, there's a certain thickness which is being exposed, and that's controlled by the optics. But you can see that in this case, like they made some very, very fine features. You know, you could optimize the system if you want to make very, very thin layers. But remember, the thinner the layers are, the longer the more layers you're going to need to make your device. This slide is talking about direct laser lighting. A little bit more about this. So we talked about micromirror arrays, which is projecting a pattern. This is going back to talking about direct laser lighting. Now, again, like with the laser scanning, you have to scan that laser back and forth, raster scan it, so it takes a long time to create an image. But one trick you can do with laser writing is that you can get very small features by using what's called multi-photon lithography. So remember, the basic concept is still the same. The region that you are... It's not liking this. There we go. So we have a laser system here. The laser is bouncing off this mirror here. These are just some optics. This is an optical modulator to turn the laser on and off. Some more optics to focus the laser and so on. And ultimately it goes into this microscope objective where that laser is being focused down to a very tiny spot. Okay. The spot is remaining in the same place. The sample is mounted on a three-dimensional piezoelectric stage. So the sample is moving around, but the laser spot is staying in the same place. Now, the reason you can get very small features when you're working with a laser as opposed to a DMD is you can use this thing called multi-photon polymerization. Now, you'll choose a wavelength where the material is mostly transparent. So you have a photoresist here. You'll choose a wavelength which does not really absorb the laser wavelengths very much. Okay, well you might think, well, why would you do that? Like you want the light to be absorbed so that it causes that cross-linking, right? If you choose a wavelength where it's mostly transparent, then most of the places, even where it's exposed by the laser, will not be exposed. But this laser beam, you can see example of it here. A laser beam, when you focus it down, it creates a beam waist, a very narrow region, right? Like you can see here. Now, if you use this approach, what will happen is the resist will only get exposed in the regions where the beam is very, very tightly focused, where you have the most photons coming into the system. Most of the photons are passing through, but in the region where the laser beam is very tightly focused, in that region you will get some cross-linking. So the scanning laser will cross-link the resist the same as before, but when you use these multi-photon techniques, only in the absolute center of the laser will get exposed. So you can make very, very fine features this way. The diameter of your beam, let me just draw this in a schematic here. So let's say your laser beam is being focused this way. Now when you focus a laser beam down, typically it looks something like this, where it's sort of like a cone, and it has a waist here like this. Okay, so the substrate would be here, and this is your laser. We call this a laser cone. And let's say this is your layer of photoresist. Now, with the conventional thinking would be that wherever this, let's see, this layer of photoresist like this. In conventional direct laser writing, wherever this beam hits the photoresist, those are the regions that are going to be exposed. Okay, but with multiphoton, the multiphoton approach, only the region right in the middle of the beam will be exposed, because that's where the highest intensity is. Only at the regions of highest intensity will you get enough photons being absorbed in the material or generated in the material to cause the cross-linking reaction to happen. So even though the beam diameter might be several microns, the spot that's exposed and cross-linked is much smaller than that. It's a very nice little trick that you can do with lasers that allows you to get extremely small feature sizes. Look at this. This is a soccer ball that they made, and you can see that this dimension here is 2 micrometers. Okay. This is an Eiffel Tower, which is pretty cool. This is a company called Nanoscribe that created these images. They have a tool, a direct laser write tool, that they can make very, very small features with. This is a tool sold by OAI. It's an American company. You can see that the spot size, the laser spot size here is 0.5 microns to 100 microns. This is a more conventional tool that you can use to make objects that are either really small or even really large. So you can tune a lot of the parameters. The idea here is the same. I just wanted to show you what a commercial instrument might look like. And these are the specifications. It uses lasers ranging from 325 to 445 nanometers. You can get features down to 0.5 microns to 100 microns. If you make your laser spot size large, you can expose larger areas at the same time. So if you want to make larger objects, you would go ahead and do it that way. And you can see some of these other specs here. Typically, what you do is you'd give this instrument your CAD file, basically it basically shows where you want to expose and not expose, and the system will do the rest. Very simple. You don't need to go out and have a mask made. You can just do the writing there, which is quite nice. This is another example showing a multi-photon lithography with DMDs. In this particular example, they are combining the multi-photon idea that I showed with lasers on the previous slide with the direct laser, with the DMD technique that 2 slides earlier. So what they do is they have a laser beam here at the top, okay, and the laser goes through a galvo. So the laser is a scanning laser. It goes through some optics, bounces off a DMD. Now the DMD has a pattern on it. You can see that this pattern of 4 is just shown there for illustrative purposes. So the laser is scanning over the DMD array, but the DMD array is only reflecting the lasers at certain pixels. So that image then gets transferred over into the sample here. And they have a system where they build things up layer by layer. There's an elevator type thing here, same as before. So this system allows you to make, again, like some pretty complex three-dimensional structures. They made skull and crossbones. I don't know why they did that, but it's pretty neat, like 10 microns in size here. Now these structures were actually made out of photocross-linked BSA. BSA is bovine serum albumin. It's a protein. So it's actually showing that you can use these laser write methods to pattern proteins directly. They had a special type of formulation of bovine serum albumin. By the way, albumin is one of the most abundant proteins in your blood, just so you know. They had a version of, they chose a laser and a version of BSA that could be solidified, cross-linked using a laser. So these structures were actually made from BSA in the non-cross-linked areas, the ones that were not exposed. Basically, they washed away, and they were actually able to show some. Biological assays where cells were compatible with these types of materials. So, the conventional approaches of lithography that's used with the conventional type of lithography approaches which are used for semiconductor manufacturing may not work so well with BioMems type devices, but people have found a lot of interesting alternatives. So I think that's a good ending point here, because what we've done here is we've gone through this first part here. We've answered this question: how can we pattern a material using light? So I wouldn't say we've answered it completely, because there are dozens of photolithographic techniques. There's dozens of new materials, light-sensitive materials coming out every day. Literally every week there's new materials published. But this will give you some ideas on what the general principles are. Okay, that you can use two-dimensional techniques, you can use mask-based techniques, you can use mask-less techniques. There's a thing called the Rayleigh diffraction limit, which limits the smallest size that you can make. So with optical techniques, you can get things down to 10 to 50 nanometers. But with electron beams, if you focus them well, you can get down to even much smaller than that. There's something called focus ion beam that I haven't talked about, where you use a stream of gallium ions. That can get down to even smaller sizes. But the ideas are the same. You have light, and the light exposes a light-sensitive material. That material either can cross-link in the presence of light, or in which case it becomes insoluble. That's a negative resist. And or it could undergo some other chemical change, a breaking of the polymer, a chain scission, which will cause it to become soluble. You can change the chemical properties by adding light into the material. So in Monday's class, we're going to start talking about how can we transfer the photoresist pattern onto an actual material that we'd like to work with. Because we don't want to make all our devices out of photoresist. We would like to make them out of silicon. We'd like to make them out of metals or plastics and things like that. So we can transfer the pattern that we made in photoresist onto another material that we're working with. So we'll talk about hard materials next class, and then the following class probably we'll get into soft lithography. All right, so in terms of the homework, get started on the homework this weekend. If you have any questions, please let me know. I haven't had a chance to make the correction on that homework yet, but I'll do that this weekend. But you can get started on the other questions in the meantime. So, any questions? Any questions before we end today? Okay, good. So another point I want to make is that, you can see that this class is, last module was a lot on physics and scaling laws, and this one is completely different. It's on fabrication. So you're going to get a taste for different different ideas, different concepts in BioMems, because it is a very interdisciplinary field. But I think you'll find it pretty interesting. So that's it then. Well, I'll see you all on next Monday. If you have time over the weekend, think about project ideas. The sooner you start thinking about it, the sooner you decide on a project idea, you can actually start reading about it and thinking about it. We will have different parts that will, I'll talk more about that in the coming weeks.